Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
Hello, everyone, and welcome to another edition of Ask Us Anything About Electrochemistry. I am your solo host today. I'm Dr. Neil Spinner. I'm an electrochemical engineer here with Pine Research, and my trusty co-host Alex is out today, so I am just hosting this myself. But thank you for joining me, for those who are, and if you're watching this after the fact, I hope you enjoy whatever questions are coming. I don't know what they are, except for a couple I have from, I guess, last week. I don't think I was here last week. I was at the Electrochemical Society meeting in beautiful Honolulu, Hawaii. So for anybody who happened to come by our booth or just was there and not working, because Hawaii is one of the most beautiful places on earth, I hope you had a good time. But the meeting was very nice. It was nice to meet some people in person at our booth, and some people had mentioned that they watched some of our YouTube content or webinars or podcasts. So it's always really nice, and it's, you know, for me personally, I enjoy meeting people who mention this. It's nice to hear from folks who are enjoying the content that we're making and putting out. So we'll keep doing it as long as people are enjoying it, I guess, and it's useful. So in any case, this is an event where you can, as the title suggests, ask anything about electrochemistry. So whenever, if ever, you have a question, you can type it into the chat. We have perhaps you're watching on YouTube, on Twitter, X, or LinkedIn. We are, I think, simultaneously streaming on all of those. This is my first time doing it without Alex doing all three at once. I think he got that going last week. So I actually don't know if I've done this. We've upgraded sort of everything to be simultaneously streaming everywhere. So it's kind of exciting, to be honest. But, you know, as with most things, when you start increasing your technological output and everything, it can be a little nerve-wracking if you're not you know, haven't done it before. But in any case, if you do have questions, type them anytime, and I'll get to them as quickly as I can. But as I said, there are a couple of questions, and I'm going to get to these that I think Alex had mentioned were from last week, or perhaps you know, maybe been a comment on a YouTube video of some sort, but I'm not 100% positive. In any case, I'm going to answer these, and you know, if you are the person who had asked this, I hope that you eventually see this, and if not, hopefully it is maybe relevant to some of you out there. And so the first one is from a user, I think Tim Lin 3149, and they asked, what is the value of performing EIS at non-faradaic biases versus faradaic? Can you learn something meaningful, and or should EIS always be performed faradaic? So this is a good question. EIS does not always have to be performed like faradaically or with a faradaic reaction present, right? There's nothing intrinsic about impedance that requires you to have a faradaic reaction occurring. Okay, I'll try to draw a couple of examples here. Let me pull up this, and I'll have to make sure that I am sharing. I'm going to put myself, am I in the corner? Yeah, I'm going to hide the question so you can sort of see me there. There we go. I think hopefully you're seeing everything that I'm drawing and you're hearing me, and I'm not, as I say, talking into the void. But when you have a faradaic reaction, right? Let's say, you know, A plus N electrons goes to B. So we have some Faradaic reaction, whether it's the oxidation or the reduction, as I have it written, right? When you do impedance on something like this, if you pick a potential, this has some, let's just say E0 equals, whatever, let's just say 100 millivolts. So if I do my bias, let's say EIS, let's just say EIS baseline. Let's say I pick something like I want to do the oxidation reaction. So I'm going to pick something positive of this. So I'm actually going to go from B to A. So it doesn't matter whether it's the oxidation or reduction, but just for instance, let's say I pick 200 millivolts, whatever the reference is, it's not relevant at the moment, right? So I'm picking a baseline. So I'm doing a Faradaic reaction. Now this, of course, is not every single reaction won't exactly behave the same way. But just as an example, when you do a Faradaic EIS experiment, when you're studying an experiment and how it reacts Faradaically, when you look at the Nyquist plot, you usually will see something like a sort of typical Randall's behavior. Again, it really depends on what you're studying, but in general, you'll probably see a semicircle and you might see some diffusional behavior at low frequency. And, most commonly you'll fit this with a ohmic leading resistor. Let me draw this the right way, I guess. Resistor down here. We'll put a CPE up here. It could be a capacitor or a non-ideal capacitor, either way. And then you'll have, often a Warburg element for the diffusion down here, right? And that's sort of the simplest, most basic kind of analysis that tends to happen for when you're doing impedance of with a baseline of a Faradaic process, right? And this part right here, the R and the C or Q, this is, this semicircle, right? I'm trying to draw an arrow, but I'm not drawing very well. There we go. So that is the charge transfer process and the double layer capacitance usually of this reaction. So you're studying the Faradaic process, the charge transfer, the electron transfer. All of those things are what are being probed when you do impedance at a baseline where you have a Faradaic reaction, where you're actually studying it in this way. Okay. Now, conversely, if I have, let's just say non-Faradaic. So that it means one of two things, right? Either I'm picking a potential where this reaction is not happening, or I just, for whatever reason, have a electrolyte and a I don't know, setup where I have nothing, no redox processes present. Like it's just, you could imagine like a glassy carbon electrode in sulfuric acid, right? And there's no alcohol to be oxidized. I'm not going to the oxygen, evolution reaction. I'm not going to the hydrogen evolution. I'm staying right in the middle potentials. It's like just non-Faradaic. It's like capacitance. There's nothing else. You will usually see for a non-Faradaic reaction just something like this. Sometimes it'll be a straight up and down. Sometimes it'll be like at an angle. Sometimes it'll be a straight line. Sometimes there'll be a little inflection, but mostly you'll just see this. And typically what that is just something like you'll have a leading resistor because there's always ohmic resistance, but you might just have capacitance, or you might use a CPE if it's sort of non-ideal capacitance, which is pretty common, right? You might have something like this because you can't really ever escape a double layer. The electrochemical double layer forms on your electrode surface. I mean, that is always going to happen pretty much no matter what you do. But the point here is that both of these are ways to study electrochemistry or your electrode, right? In one case, you're getting information about the charge transfer resistance of the Faradaic process, maybe some diffusional behavior, as well as the capacitance, let's say, of your double layer. In the other case, you're basically just getting ohmic resistance and information about the electrical double layer, the capacitance, etc. But in both cases, you're still studying something, right? And it's perfectly valid to study both Faradaic and non-Faradaic processes. For instance, things like supercapacitors or capacitors or whatever in that field is all sort of fundamentally non-Faradaic processes, right? I mean, you're studying a capacitance of the material to see how good it is, right? You do cyclic voltammetry for that. You might do impedance for that. So using this non-Faradaic kind of impedance is what you're after, right? There may not even be anything Faradaic to study, and that's by design. So again, I guess sort of the summary of that is that both are perfectly valid. You can absolutely study Faradaic and non-Faradaic processes. And it just depends on what you're interested in. And then the last thing that I'll say to this point, which is something I do get questions about, I don't know, somewhat frequently, and it relates to the bias, because your question said, right, Faradaic biases, non-Faradaic biases versus Faradaic, because a lot of the ways that this question takes a form when I get asked this is that people will say something to the effect of, what potential should I do impedance at? And I actually like this question because it kind of answers that question like in a backwards way, which is to say, if you're asking what potential should you do impedance at, the answer is, are you trying to study something Faradaic or non-Faradaic? When you answer that question, you will get the answer to what potential you should do impedance at, because a lot of people just sort of naturally do impedance at open circuit potential, and they don't like recognize that they can do other set potentials. And frankly, at open circuit potential, most of the time it's non-Faradaic. Like might be some situations where you have some Faradaic response at OCP, but very often not, because you're at open circuit, and quite frequently you have to polarize positively or negatively to a certain degree before you start seeing anything Faradaic. And so it can be really important to recognize what you're trying to study, whether it's Faradaic or not Faradaic, and then make the choice of your baseline at that time. So thank you for that question. There are a couple others that I have, again, sort of from last week, and then one from just earlier before this event started. I see there are some live, so I will try to get to everything. I want to answer the one from Wajiha because it looks like they asked it just chronologically first. I do try to answer the questions chronologically first, and I'm just going to bring up this question, which was a saved question from apologies again if I mess it, Sarfazamad 2143, and because it's related to the question that Wajiha had asked. So this person asked how to determine the potential window for cyclic voltammetry or galvanostatic charge discharge, and then again the question that chronologically was first, I will try to answer now, and then I do see Mustafa and Amena and Tubai and Malikzad. I see your questions. I will get to you, I promise. But I want to address this because, again, this was first. So Wajiha said, can you explain GCD? And so I'll try to touch on both of these questions at the same time here. So that stands for galvanostatic charge discharge. I can't find material that's simple enough to understand. And then the second part is, what is the application of EIS in biosensors like glucose sensors and in supercapacitors? So I've sort of already answered the supercapacitors part, the last part of your question. What is the application? Very frequently, it's to do impedance on that non-Faradaic process of supercapacitors, supercapacitance, capacitance, whatever terminology you want to use, and to gain a quantitative measurement through the circuit fitting analysis to try to measure the capacitance, right? And so similarly to what I drew, here for my last sort of explanation, you have this capacitor here. Let's just say you're studying the impedance of a supercapacitor. You're getting a value for this capacitor, and then that's what the study is. But let me get into galvanostatic charge discharge a little bit, because I think this is a good question, and I'll talk about the potential window as well. So when it comes to the potential window, let me touch on that first. To determine the potential window, very often CV is a better option than GCD, but you're going to use the limits in GCD. So for CV to determine the potential window, let's just take water, for instance, so aqueous solvent. Most of the time, if you go very far negative, so this is potential here, right? And this is current on the y-axis. So if I go minus, let's just say minus 2 volts, plus 2 volts, it's probably in this range, more like -1 to +1 or -1.5. It really depends on the reference electrode, depends on the pH. But let's just say, roughly speaking, if I go really far negative, really far positive, if this is, let's just say this is 0, just put a baseline in here somewhere. As I scan negatively, it'll really shoot down, right? And then as I scan positively, it'll really shoot up. So obviously, depending on what you're studying, there might be a peak in here. There might be different behavior. If I do a CV and I sweep back, I'll have some band, some window. Okay. The point here is that when you're trying to find the potential window, a lot of times what you're trying to do is find the points about which I'm observing like behavior that I'm interested in. And so, quite often it's like, well, what I want to study is in here. Here I'll have, this is like electrolyte breaking down, maybe oxygen evolution reaction. Here I have the electrolyte breaking down in the other way. I have hydrogen evolution, and the current becomes really, really aggressively large in either the positive or negative direction. And so finding the potential window is usually done if you don't know like anything about your system in an iterative process. So you're going to do something like, okay, I'm going to pick these limits here, right? And I'm going to do a CV and just go back and forth between these limits. And you're like, okay, well, that looks fine. All right, next, I'm going to increase the limits a little bit, right? I'm going to add 200 millivolts on either side, and I'm going to just do another CV. And it's like, okay, well, I get a nice, window like this. And like, that looks flat and nice and easy. And then I'm going to start decreasing both ends, right? And eventually it will like start dropping, maybe on one end. Maybe it only drops on one end and only a little bit on the other end, or something like that. And so I might say, okay, well, here, right here, this is my, E1, like my lower limit. And then I do, one last CV up to here, and I find that that's where it starts peaking up. And so it's like, all right, well, then I might cut it off here, right? So I'm being very general. I'm not giving any like specific numbers because it's going to depend on a lot of factors. But this might be a way to iteratively kind of slowly increase the limits on both ends until the current starts, beyond the region where it's things of interest. Now, again, there could be peaks in here that I'm not drawing. It depends on what you're studying. So that's not really the point. It's more like when you're hitting the limits of your electrolyte very often, that's where you're finding the limit there. Now, galvanostatic charge discharge is something that's used more frequently with batteries or sometimes capacitors. And it's distinctly different from cyclic voltammetry, particularly in that cyclic voltammetry is a potentiostatic technique, and GCD, that is a very narrow text box. Galvanostatic charge, sometimes charge discharge. Let's make that a little bigger so you can see it. All right, great. So that's what GCD stands for. And in the name, you can see galvanostatic. It's a galvanostatic method, which means I'm control current, and I measure the potential of the voltage. And so because I'm measuring the voltage, I have to know where and when it matters, where and when to stop, right? So typically what this does, or what this experiment looks like, another name for this is something like chronopotentiometry. So I'm measuring the potential over time by setting the current. And so whereas with a CV, I'm plotting So with a CV, for example, I plot potential down here and current over here. For GCD, instead, I plot potential on the y-axis. So I'm putting it on the opposite axis. So I'm going to put these in parentheses just to remind you where CV plots stuff. But with GCD, it's opposite. So potential goes on the y-axis, and then this axis is actually time. Okay, and so I'm studying how the potential changes over time. Fundamentally, that's what you're doing. Now, this gets transformed into a capacity, usually if you're doing batteries. But fundamentally, what I'm looking for is potential versus time. Okay, and considering here what I just showed you, for example, I've determined that E1 and E2 are the limits of my potential. What I'm most often doing is I am taking this would be E2 if it's the upper limit, and this would be E1 if this is the lower limit. And I apply, I equals whatever, plus 1 milliamp. It doesn't, whatever the number happens to be, right? And I'm going to watch the potential change over time. And it will, maybe let's say it increases, and then maybe eventually it sort of goes up and hits my E1, right? And so I'm going to, most of the time, what you're doing is you're stopping it. And then you'll do the opposite. Let's just say that's a charging experiment. And then you'll do a discharging experiment. I is equal to minus 1 milliamp. And so the voltage will probably drop and then maybe flatten for a while and then hit the lower limit. And I'll stop once I hit the lower limit. So I know the limits of which I'm trying to let the voltage go, but the voltage will go up and down, up and down. It takes a certain amount of time for that to happen. And typically I'm doing it at a constant current. So that is, now, in a similar way to what I just showed here in CV, you can iterate over and over again with CV. It's a bit safer and more controlled to find those potential limits. You can find the potential limits with GCD by just applying one current and watching the shape of the curve. And once usually the GCD curve, if you have a good battery or capacitor of constructed, the current the voltage will change an inflection, right? Like it will start to increase and then it will shoot up or shoot down, right? It kind of takes a sharp turn, and that can be a way for you to determine, okay, well, when this shoots down, I should cut off the voltage there, and this shoots up, I should cut off the voltage here. That is another way to do it, but typically galvanostatic charge discharge, you want to already know, if you can, the limits of potential before you start, because it's usually a safety thing. You're trying to charge it up and charge it down, and you're trying to keep it within a voltage range that is specific to that charge discharge process. Okay, so I think I have addressed those questions, and I do want to get to the live ones because I see there are a few, so I don't want to keep people waiting too long here. Now, Mustafa has asked, on the surface of carbon cathode in a supercapacitor, what is preventing electrons to combine with ions in the electrochemical double layer capacitor, despite the activated carbon can conduct electricity? On the surface of the carbon cathode in a supercapacitor, what is preventing electrons combined with ions? Trying to think of a good way to answer this. The answer might have to do with the mobility of electrons. For instance, of course, the activated carbon can conduct electricity, but if you think about the double layer capacitor, let me pull up. I actually have a better. Let me see here. This was a webinar I gave 2 days ago, I believe. That would be the date. So the double layer capacitor. Let's see, is this showing? I think it is. It is not. I'm sharing the wrong window. Let me share. Stop screen sharing. Let me try to share my screen. Hang on, I'll share with you something here real quick. I'm gonna do this presentation mode, and then what I want to do I want to see. Give me just a moment and I will get this to you here. That's not it. It's tougher when it's just me. You know what I mean? It's easier when there it is, taskbar. That's what I wanted. All right. It's easier when Alex is here with me. He can kind of help make sure I'm doing the right thing. Okay. This is hopefully the right thing to share. So, taskbar. All right. I think I'm sharing. This is the double layer capacitor. So, in solution, for instance, we have an electrode. So this is an electrode. Let's say this is the activated carbon right on the left here, this electrode. And on the right, I'm going to hide the question so you can see what I'm talking about. So we have like water and KCl in here, right? And we have lined up over here, we have, for instance, to your question, you have like a carbon cathode or whatever the material is, and there's ions lined up next to it. Now, what prevents electrons from combining with these ions? Well, there is a physical distance here between the lined up ions and the polarized electrode, which is in your case a carbon, whatever, activated carbon. Fundamentally, whether you think about it in terms of the electrical double layer, the EDLC, or just solution in general, electrons don't like tunnel through solution that way. It takes a tremendous, like you can think about it when you're doing electrochemistry, even fundamentally. Try to put it a different way. When you have electrochemistry, I'm going to draw this for you here. I have, for instance, a solution with electrodes. Okay, I have a working electrode. I have a counter, right? Electrons go like between the two through your potentiostat, right? So they go whatever from the reference to the counter, from the working to the counter, or vice versa. Electrons don't go like in solution from like that's not what happens, right? It's ions, positively charged or negatively charged ion, like potassium or chloride ions. That's how the charge is balanced in solution. This is sort of fundamental electrochemistry kinds of principles, I guess you'd say, is that the movement in solution. So if you're asking in the electrochemical double layer or in solution itself, why don't the materials or the ions combine with electrons directly? Because electrons stick around the surface of metals, which are your electrodes, and then they travel through the circuit through your potentiostat. Electrons don't like jump into solution. It would require a tremendous voltage for that to happen. That's not really fundamentally how it happens. And then the other answer I would say, I guess, is that the double layer itself is a capacitor, right? Where I have like ions lined up from the carbon. And so these are, whatever, these are my ions. And this is the inner Helmholtz plane. And these are the ions. So fundamentally, this is a capacitor because there is a distance between these two planes, right? A capacitor are two parallel plates separated by some whatever distance d, and there's some surface area a, and there's a dielectric of water material, whatever. And the fact that you have that show up means it is a capacitor and there is a separation and it's a dielectric material. And if electrons could jump directly between plates in a capacitor, whether it's like a real capacitor or an electrochemical double layer, and electrons could just jump in between the two, oppositely charged plates, you wouldn't have a capacitor at all, right? I mean, think about it. It's like if that could happen, capacitors wouldn't even be a thing. It's just that's just not how it like it's almost like the answer to the question is kind of like it's just fundamentally not how a capacitor works. It doesn't. Electrons don't just jump in between the plates. It can't like physically work that way, I guess. So I guess that's kind of the way I would answer that. I hope that kind of clarifies it a little bit for you. let's see here. Amin has a pretty lengthy question here. I know not all of it is showing up, but I'll try to read it here. So number one, is there any reproducibility issues in measuring hydrogen peroxide? Hydrogen peroxide, okay. When doing amperometry in nanomolar range by screen printed electrodes? Probably, but I suppose it depends. How about modified screen printed electrodes with mediators like Prussian blue? So probably, I don't 100% know. I mean, I probably have to do the mathematics out, I guess. You can use like Faraday's law of electrolysis, for instance, um, to determine like convert charge to moles of species. Like if you have X amount of amps or milliamps or microamps, right? And using Faraday's law of electrolysis, you can convert that to how many moles of, um, let's just say peroxide were reduced or whatever it is, whatever the reaction is. For example, usually it's like peroxide to water, and I guess what you release oxygen gas or something like that. In any case, you can sort of make that assumption. But nanomolar range probably is going to be tricky because it's going to depend on the surface area of your electrode. And screen printed electrodes often have pretty small surface areas. So I don't know enough about like Prussian blue specifically. Like if it's a really well, I don't know, active modifier for or mediator, whatever the right term is here, for a screen printed electrode that like facilitates peroxide measurement, for instance. That may be the case, but the only two ways to improve your signal, let's say, I guess, signal to noise ratio, let's just say, would be to improve the catalytic like activity or reactivity, right? By using a mediator. In this case, Prussian blue, I suppose, if it works in that way. I don't have experience with it. Or to increase the surface area, because if you increase the surface area, you'll increase the amount of current you get, and you might, I suppose, increase the amount of stuff you can detect or react. Now, if you have like nanomolar range of peroxide, detecting it might just be fundamentally difficult, because one of the problems with what I just suggested, for example, is that if you have a very large surface area, you'll get more current, but a lot of that will be background current. And if you have a really high background current, you might not be able to even like detect the signal for the peroxide like above the background. You know what I mean? The background might be really high. And so that could convolute your measurements perhaps. I can't speak perfectly well to like what, nanomolar or micromolar or millimolar, like what is there some limit? There probably is some limit in general for, a certain setup or a certain reaction. I don't know off the top of my head without, I guess, sitting down and doing some math. And I'm not going to like sit down and do math in front of you all and waste your time, I suppose. But probably you could calculate like a reasonable amount of surface area, how much current you get and how many moles can be detected, something like that, to what would be, I guess, possible. So that's how. So, and again, I suspect nanomolar almost for sure is going to be near or below the limit of what you can measure. I do suspect probably you're going to have reproducibility struggles. It will be probably quite difficult. It's just my guess. And then number two, you say, when you do amperometry, how do you choose the right potential for measurement? Consider hydrogen peroxide. You do CV, you're confused. What would be the difference between applying anodic or cathodic peak potential? Should I apply exactly peak potential or higher? So if you're trying to like completely run the reaction, right? And peroxide, is it? I think it's reduction. Isn't it a reduction? I'll try to like look this up. Peroxide reduction. Yeah, I think like if you add a couple of electrons to peroxide, it's like an alternative to you'll make water. So maybe let's just say it's a reduction reaction. I'm pretty sure that's the right way. But if there's an oxidation, I'm just forgetting off the top of my head here. I'm trying to speak more generally, so my apologies. I would personally pick, if I'm trying to like really drive it like hard, you know what I mean? Like drive the reaction and really reduce, in this case, the peroxide. I would pick, for example, if I have a peak, let me draw it rather than pointing into the sky here. Here we go. So let's say, it probably doesn't look exactly like this, but I don't know, maybe it does. Maybe you do your CV and you have like some peak, and let's say this is, the H2O2 reduction. So I'm just making some assumptions here. If I'm thinking about like what potential should I pick for chronoamperometry, what potential should I run it at to like really drive the reaction, I would pick something on this side of the peak. That is going to establish most probably a fully irreversible situation. So, if you think about the peak, if it's reversible, for example, if you had a peak going this way, if the other way, for example, then the E1 half is here, it's halfway between peaks. So whatever the standard E is, E0 of this reaction, it's something, what is it? It's like 120 millivolts ish. If you're like more than 120 millivolts beyond the E0, that's roughly irreversible. You get roughly 99% one way and 1% the other way. So it's like assumed to be irreversible, something like that. So basically it's like, if you have this peak and you pick something here, this is probably like, if this E0, is 0, then you're picking this point as like, let's just say minus 200 or something like that. And that's going to like, again, fully make that reaction run like with a large enough over potential that it's like roughly irreversible. And then, you'll have a background current for your chronoamperometry. You'll have to sort of take that into account. You'll have a double layer. You'll have, when you do your chronoamperometry, you're going to have a decay probably, right? No matter what. And you might have, again, this sort of background current here. And take that into account. But if you can make an appropriate subtraction of your background current, you can get a steady state kind of faradaic current from the reaction of interest, which is the reduction of peroxide. I would pick something that's rather large enough if that's what your goal is. Okay, I think I've covered that hopefully relatively thoroughly. All right, let me see here. Try to make sure I get to everybody's questions. And thank you again. I think you last two questions came from LinkedIn. So very nice to have you joining us there. All right, so Tubai has asked, can you explain 2D diffusion and 3D diffusion from chronoamperometry? Good question. 2D diffusion and 3D diffusion from I don't think I know if 3D diffusion is like possible to extrapolate. I'm trying to think, like the diffusion, I guess I don't think about it very often. I guess it would be 2D. You're sort of describing the diffusion of ions like to and from the surface, which is sort of implicitly two-dimensional. I don't really know if there's like a 3D diffusion. To do that, you'd probably have to have a some sort of a simulation, mechanism worked out. But for instance, when you study, try to do this quickly. This is our software Aftermath Blue. I'll try to do like a simulation. So simulate bulk electrolysis. So this is like chronoamperometry. I'm just going to pick something kind of quick and see if I can just make a very. So here's just some bulk electrolysis. I want to try to give me just a second to sort of simulate and work through some stuff here. I think that, for example, in this case here, just for instance, Let's see if I want to kind of get the surface concentration to, if I can do anything. What you see here is it's kind of decaying very fast. That's why I'm trying to, maybe I can do like 1 second. I don't know. I want to see if I can get anything to look a little bit more interesting, if you will. What is the E0? 0. So I'm just simulating a very simple kind of electrochemical reaction here. I'm going to try to slow down the diffusion coefficients. Maybe that does a thing. I'll try to change my applied potential. So yeah, I won't play with this too much more. I don't want to belabor the point. But this is simulation, and I would have to tinker with this to kind of get the perfect example for you. And I guess I'll sort of just stop for now. But suffice it to say, most of the time, I believe, with chronoamperometry, you're looking at 2D diffusion, right? Like this, for example, are showing you plots of the current versus time, right? For a chronoamperometry, for instance, it decays one way or the other depending on whether you're doing oxidation or reduction. But the surface concentration will the diffusion and the surface concentration will be it's two-dimensional. Like this at this time and this distance from the surface, you'll see a concentration profile. You'll see it start to change. So you can probably see this animating a little bit here on the bottom part of the screen. This is like over time, distance from the surface of the electrode. Let me move myself. I wonder, is it this one? Yeah, so you can see the bottom here. See how it's simulating? It's like changing actively. This x-axis is the length. So this is like diffusion from the surface of one species sort of going to low, from low to high, high to low concentration, the other going from high to low. As time goes on, let me play it again for you so you can see that, right? This is all 2D. Now, there may be a way to like extrapolate three-dimensional diffusion, but I'll be honest, I don't know if I totally know how to do that, and it might require, I don't know, a special kind of modeling and like more like differential equation solution or something really, really fancy like that. So I think 2D diffusion is definitely possible, and 2D sort of surface concentration can be done quite easily, as you're seeing here. As far as 3D diffusion, I don't know if I know how you would do that. Perhaps it's possible, but I don't know if I know, or if I have the tools to know exactly how that is done, especially with just something like chronoamperometry. Okay, let's see. Next we have HDY. What is it? Malexad. Will you have more webinars about circuit models? Oh, it's just a question about the webinars. Yeah, thank you. If you did join my my last webinar, I definitely appreciate it. Circuit models in addition to, yeah, October 16th. Yeah, 2 days ago I did a webinar. Thank you for anybody as well who joined me. Yes, I will have another webinar. It won't be next week. What is it? I'm looking at a calendar right now. So the 30th of October, I will have another webinar. I'll make an announcement. I'll probably make links like on our website. I'm going to put that link in here actually, just as a, since you asked, I don't feel so guilty. Here's a shameless plug, I suppose. So this is my this is the link to, I'll put it in different platforms here. That's the link to like my registration, the registration page for my webinars. So you see that it has the links to the one that I did on 2 days ago, and that will update probably within a week. I'll update it to have the next one and the registrations there. And that one again will be on the 30th, and I'm going to talk about things like Warburg elements, finite and infinite, as well as corrosion models. So I'll talk about some more, and then into November I'll have 2 more EIS webinars, so stay tuned for those as well. I'll be doing some circuit fitting tips and tricks, as well as some live experiments. So those are the next couple of webinars over the next, I guess, month or so. So thank you. Thank you for that. Can I please explain EIS? I can. It's a bit of a general question, right? I think one of the things that we like to try to suggest to folks is to ask questions somewhere in between very, very general and very, very specific. And this is a bit general, right? In fact, the last question was kindly asking about webinars, and I have several hours of webinar content on our YouTube channel, where I've tried to talk through impedance theory and basics and signals and plotting and conventions and validity. And then what I gave my webinar 2 days ago was on specific applications. So is this good up? I think what I will do is skip this for now. I will try to get through the other questions that are a little bit more targeted, I think. And if there is some time at the end, what I will try to do is maybe talk through a little bit of like the slides from my previous impedance theory webinar. I'll try to just show, if I have some time, the basics of how you do EIS. But I think I'm going to skip for now. It's a bit too basic, and I don't want to spend too much time giving repeat content that I've just given in a webinar. So you can see that on our YouTube webinars playlist. Paw Mining says how to calculate the redox potential from the peaks of cyclic voltammogram. It's actually usually quite simple if your CV is behaving itself, which is not always a guarantee. But if the CV is relatively reversible, the redox potential is very briefly halfway between the positive and negative peaks. So if I have a CV, for instance, and I have potential down here, and I have current up here, and let's say I have a reaction where I'm going to take my time and try to draw it nice. Alex is usually better at this than me. And I have a positive oxidation peak, and then I scan backwards, and I have a negative cathodic reduction peak, and I want to know what the E0 is. We usually take, for instance, this E right here, and then the other peak. And what we do is we go halfway in between, right? So practically, we go halfway in between. And this right here, this point, you sometimes see it listed as E1 half, E1 half. And typically that is where people usually equate it with, E. It's actually not E0. It's more, let me back up for a second. So the Nernst equation shows that E is equal to E0. It's minus RT over NF natural log of Q. Is that right? Let me make sure I wrote it right. I always feel silly if I wrote the Nernst equation wrong. Plus, Alex will never let me live it down because it's his favorite equation. E is equal to, RT over NF. Yeah, I wrote it right. It's minus. Okay. I was making sure the signs are right. This is the standard reaction potential. And this is like, this would be like the measured, like this E right here would be that E. Sorry, I know that like arrows everywhere. This E right here is this E, is this. So like what you're doing is you're measuring practically. This is like the what did your question says, the redox. I just want to read the redox potential, if you will. That's like specific to your system, because the E0 in the Nernst equation right here is a thermodynamic quantity that's related to the Gibbs free energies essentially of the products and the reactants, basically. And so in real conditions, we have ideal gas constant, temperature, number of electrons transferred, Faraday's constant, and then the reaction quotient, which is actually related to the activities or the concentrations of your things and species. That is affected by pH as well. So all of these sort of experimental conditions cause you to get a real measurement of E, which you can calculate using the Nernst equation, or as I'm showing here, you can just basically take halfway between the peaks, the oxidation and the reduction peak, the anodic and the cathodic peaks, either way. And that E1/2 is usually what we consider to be the redox potential. Okay, Sudeep says, please explain the Butler-Volmer equation, especially with anodic and cathodic sign notations, getting confused with concentration and current terms in the equation. Sure, I'm happy to do that. I think let me get another PowerPoint presentation. I don't have enough open right now. I have only 3. I'm going to close some of them. I have too many open. Makes it confusing to make sure I don't have too many open. All right, I will open and show you the Butler-Volmer equation. Just give me a second to find it. It is here, and it is here, and it is... I'm going to pull up this one. It is in my slide here. That one. Okay, sorry for the delay. So the Butler-Volmer equation, share my screen. Yeah, let me find it. This one. Okay, so this is from my RRDE webinar. All right, so the Butler-Volmer equation. So this is the kinetics. It's fundamentally an equation that describes the kinetics, right? With the anodic and cathodic sign notations. Okay, so the tricky thing about the Butler-Volmer equation, which I suppose is related to your question, is that the convention it depends on what convention you're looking at, right? So what you're seeing on the screen right now is for the IUPAC convention, which is to say, let me just zoom in a little so you can kind of maybe see it a little bit better. Hopefully it's a little bit larger on the screen. It might be a little more convenient to you. The IUPAC convention is that positive current is oxidation, negative current is reduction. Okay. And the other convention, again, which can go either way, which is tricky, is this alpha, is the symmetry, was the symmetry barrier or the transfer coefficient, and whether it matters whether it's defined for the anodic or the cathodic. Now, most of the time, alpha is 0.5. Okay, so if alpha is 0.5, it actually doesn't matter whether you're specifying it to be the anodic one or the cathodic one, because they're both 0.5. If one is 0.5, the other is 0.5. But I hope you understand, if alpha is 0.3, alpha minus 1 is 0.7. And so in the way that I've drawn it here, for instance, I think I'm saying this correctly. The alpha in this case is the anodic, because, for example, if alpha is 0.3, this first term, e to the alpha nf over RT times eta, it's overpotential, right? This is going to result in a positive value. Like this is a positive number. And so this is the part that's contributing to the anodic current, the anodic positive anodic current. So all IUPAC convention here, right? On the other hand, the second term, minus e to the whatever, this is going to contribute to a negative current. This is the cathodic part. And so if alpha here is 0.3, alpha minus 1 is 0.7. And so it's like saying it's favoring the cathodic, right? So if alpha is 0.5, you don't have to worry about what I'm saying right now. So let's just ignore alpha for a second, right? If alpha is 0.5, it's equally symmetrical about anodic and cathodic. What we have with the Butler-Volmer equation is a situation where, go to my next slide here, we have an exponential function depending on which direction the overpotential is, right? Again, we're doing alpha is 0.5. So there is a situation where e to this minus e to this for a certain overpotential is 0. Like they cancel each other out, then I can be 0, right? But if my overpotential is large enough, then what I'm going to get here is that one of these terms becomes really large and one of them becomes really small. And actually, let me try to point out one thing that maybe that'll help you. I think maybe by looking at the equation, this might answer your question. Again, sticking with the IUPAC convention, consider this equation here, right? I actually misspoke when I said alpha minus 1 is 0.7. It's actually minus 0.7, right? So think about this, okay? Let me make sure I'm showing the correct thing on screen. All right. If my overpotential, eta, right here, is very large and positive, right? A positive number, right? E to the, and alpha is 0.5. So I have e to the positive 0.5, and F and RT are all positive numbers. And I have a large positive number. So e to the positive, 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 positive. I have e to the positive. This is a big number, or some positive number, right? Look at the other term. I have alpha minus 1. So alpha is 0.5. 0.5 minus 1 is minus 0.5. Okay, so I have e to the minus, and then I have positive, 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 and eta is positive. So I have right over this whole term, this is the cathodic contribution from the Butler-Volmer equation. Right here, when eta is a very positive number, I have all positives and one negative. So e to the negative large number. Well, e to the negative 10, e to the negative 100, e to the negative 1,000,000 is like 0, right? It's 1, that's 1 over a big number, so it goes to 0. So mathematically, when I have a very large overpotential, this is a very small number, e to the minus big. So at a large positive overpotential, I have a large positive current minus nothing. So I have a large positive number. And that's why you see at a large positive overpotential, here, it increases exponentially. It goes to a large positive. Now I'll just do the opposite argument just for completion. Consider the opposite situation. I have a large negative overpotential, right? What happens mathematically? If eta here is negative, again, what's the contribution of the anodic part? I have alpha is 0.5. Positive, 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 negative. So this is e to the large negative. So now this first term is 0 or close to 0, right? It's very, very small. All right. Second term, what happens? Alpha minus 1, 0.5 minus 1 is minus 0.5. I have minus, and then I have positive, 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 and now eta is negative. So I have negative and negative. I have two negatives that makes it positive. So in summary, when my overpotential is negative, large and negative, this first term now goes to 0. The second term gets big because I have negative and negative. Now it's a positive number. So this e to the all of this stuff is a now positive number. But look, it's minus this. So it's minus a large positive number. So when I have a negative overpotential, mathematically, this term is 0 minus a large number, which is a negative large number, which is a reduction current, right? As my overpotential is negative, I have a negative current, negative large current. So there you go. That is, I don't know, maybe the best way I can try to explain the Butler-Volmer, why it goes up in one direction, why it goes in the other. It's this mathematics. It's just simple mathematics of what happens when the overpotential is large or small, how the exponents, I guess, work out, right? Hopefully that addresses that for you. I know it can get a little confusing, especially mathematics isn't maybe everybody's favorite topic. But Sudeep, if you have any follow-up questions on Butler-Volmer, please let me know. Let's see, 2x. You had asked about 2D diffusion, 3D current density versus time graph. 2D diffusion, can I explain? It's two-dimensional because it's talking about distance from the electrode surface, but not XY distance, right? Like, or XYZ distance, it's just distance. So it would be like assuming, I don't think I could draw this well enough. I don't think I'm a good enough artist. But if you imagine, like, I have a flat electrode plane, then I have like X, Y, and Z, right? Like, so what it's saying is that only one, like, from the electrode surface, the concentration, how the diffusion occurs is just the distance from the electrode, but it doesn't account for, well, it happens here, what happens here, here, here. It's only if it's just a distance from the electrode. If this whole plane, like this whole top of my laptop screen, I don't know how else to illustrate this, is the electrode surface, then everywhere above my laptop screen, whether it's the middle of it, the side of it, whatever, that is distance from the surface. It's not taking into account like over here or over here, because like if the surface of my laptop, my electrode is heterogeneous, you're probably going to get some three-dimensional kinds of impact, like the diffusion or the concentration might be bigger over here. If there's a defect, it might be smaller over here. Like those things can probably happen, but I don't know that. The point, I guess, that I was trying to make was that I don't know that like chronoamperometry is going to be very effective at illustrating that or helping you understand that, because the chronoamperometry you're doing is like a aggregate response from your whole electrode surface, like heterogeneities and all. It doesn't matter. Okay, so that's going to make it a little bit difficult for you to really, I don't know, understand, I suppose, three-dimensional effects is, I guess, the point I'm trying to make. Okay, where am I here? Hide. Okay. What is the practical significance of the exchange current? The exchange current is basically a kinetic parameter. It is probably something that is better understood as a heterogeneous rate constant. So often K, the rate constant K, I'm not sure if I showed it earlier. I can't remember. In any case, the exchange current, I always find it hard to describe. Like, it's the amount of current that occurs, like, in theory under certain conditions, but really what it is it's more like a outcropping from the fundamental kinetics of the electrode and the reaction you're studying, and it's buried in the exchange current is the heterogeneous rate constant, which is a K, like it's usually in units of like centimeters per second or just per second, something like that. And the practical significance, I mean, it's related to the kinetics, which means it's practically a metric that describes the speed of the reaction fundamentally. So in general, I suppose I would say the larger the exchange current, the faster the reaction, something like that. It can help guide, for example, the determination of like whether you have nice fast kinetics or like sluggish and slow kinetics, something like that. Would be my answer to that. Why impedance is considered in electrochemical techniques? Impedance is considered in electrochemical techniques because it allows you to do a lot of different things, including probe multiple processes that are happening at the same time in a non-invasive way by adjusting only the frequency. So electrochemical experiments, like most experiments, are done on a time scale. You do something to the current or the potential over time and measure the other, so you do something to the potential over time and measure the current, or you do something to the current over time and measure the potential. With impedance, it transforms the experiment from time-based to frequency-based, which is the inverse of time. And what that does is frequency is a rate. It's a rate, right? Kind of a unit. And what it allows you to do is probe processes that occur at different rates, because electrochemical processes like charge transfer resistance and capacitance and diffusion and all these things that we're talking about, they occur at different speeds. And very often it is difficult to study these processes qualitatively or quantitatively with things like cyclic voltammetry or bulk electrolysis or DC methods. And so when we do EIS, we do impedance, which is an AC technique. It allows us to transform into the frequency domain to study processes at the speed that they're taking place. And so we can deconvolute complex processes going on at our electrodes. So I hope that's an answer. That's kind of the beginning of my impedance theory webinar, where I talk about this. If alpha is 0.3, how does the curve shift from the Butler-Volmer equation? I'm trying to find an Excel sheet. I feel like I have one. I want to try to. I can show you how that works. It makes it asymmetrical, in short. Okay, I think I can show you here. Let me. Where is alpha? This one, blue is that one. Do I have alpha in here? 0.5. Okay. Let me share. This will be. I hope this will be Sudeep, okay for you. It's an Excel sheet, so you'll have to kind of bear with it if you're not maybe used to looking at Excel sheets too much here. Here, I'm going to move this plot. I don't want this one for now. I just want this. This is these are just different Butler-Volmer kind of plots here. I'm going to make sure that the question's not in the way. Give me a second. So here's like Butler-Volmer data. These are just what I showed on my slide, for instance. The orange one, I think, is the one that I put in my slide, like made the plot look nicer, but this is just the data. I've just basically coded, cells with the Butler-Volmer equation pretty simply here. This is for alpha is 0.5. So basically it's symmetrical, right? It goes down like here at the same rate that it goes up with the same amount of like distance in the middle, basically. If the alpha is, you said 0.3, I think. So let me put 0.3 in here, which means the first term is 0.3 and the second one is minus 0.7. Okay, let me propagate that down and show you what it looks like. Okay, so I'm going to try to, I think, you can't see it come up too much here. So let's bring this down. Bring that up rather. Maybe that'll look a little better. A little too much. Let's see. I think I need it larger. Am I going in the wrong direction? Wrong direction. Yep. Okay, let's do one. I just want it to look kind of helpful. Okay, so now forget about the blue one. Let's just get rid of that. So look at the orange one. So it just makes it asymmetrical, right? So in this case, alpha of 0.3. So to your point, right? It's alpha is 0.3. Think about what that means. The alpha in the case what I tried to describe in my slide is the anodic alpha, right? Okay, so if it's 0.3, it means it's less favored to oxidation or the anodic side, and that means that it's 0.7 for the cathodic one. So it's more favored for reduction. So this is 0 right here in the middle. And 0.3 means that it takes like longer. I have to go higher in overpotential before it starts like shooting up exponentially, basically. And then it shoots down. It's more, I'm getting more current for the same overpotential negatively, right? It's asymmetrical. I mean, it's very clear, you can see here. And so if I reverse this, if I put 0.7 for the anodic, it would shoot up like exponentially very quickly, and it would lag out here for the reduction side. So that's all it does. It just makes it makes it so you need a higher overpotential, for instance. Maybe this is a way to put it. I would need more overpotential to make this irreversibly anodic. I would need more overpotential to get the same amount of anodic current as I would overpotential in the other direction to get irreversible cathodic reaction. It's heavily slanted towards the cathodic side in this particular case. Okay. Let me see here. So 2 was still following up. If the current drop versus time, then you're saying 2D. The current drops versus time. All I'm saying between the 2D and the 3D thing is that three-dimensional effects, like certain diffusional patterns or concentration gradients or anything else, may very well be taking place on your electrode surface, depending on the position. But chronoamperometry is not probably likely to give you insight into those gradients or differences. I just don't think that it's probably likely to be able to do that. Now that you would have to do something like scanning electron microscopy, scanning electrochemical microscopy. Alex has talked about this before. I think he has done this process before. I don't have too much experience with it, but that's where you can actually take a probe and get a three-dimensional sort of map of an electrode surface. More often that I think gives you like topography or maybe activity. I'm not sure if that would even give you exactly what you're asking about, which is like more of a three-dimensional diffusional pattern. Maybe it does, but just like if you just have typical system where you have an electrode in your solution and you're just doing chronoamperometry and you're just measuring the current, I don't think you're getting very much three-dimensional information from that. I just don't think it's part of the measurement fundamentally. Concentration. Okay, so it's so deep had asked, right? Alpha is 0.3. I showed you how that changes the Butler-Volmer and concentration terms in Butler. Right. So not from concentration. There's no concentration term in the Butler-Volmer equation. Right. It's concentration is not the right way to look at it. Although there will be changes in the surface concentration, like similar to what I was just talking about with this other question. But mainly what I'm trying to show, I think, was how the current exponentially changes asymmetrically if you have alpha not equal to 0.5. So again, Sudeep, please follow up if you need more clarification on Butler-Volmer or anything like that. I think I've covered that for you there. Amira has asked, hello, what is the difference between an H cell and an electrolyzer? An H cell is just the term for any cell that is constructed basically that has two sides with a frit in between. Let me like pull up a picture just to drive it home. So I'm kind of clear about what I'm talking about. I'm going to share this one. Share H cell. So this is like an H cell that my company sells, for instance. This is an H cell, right? Just very, very generally here. You've got two components or compartments, right? And it's called an H cell because it's shaped like the letter H. and then you have a frit in between them. So sometimes you have a membrane, sometimes it's a glass frit, but basically two compartments that are separated by some physical separation that allows diffusion, but maybe slowly. Maybe it's selective ion diffusion, like you might have a Nafion membrane, which preferentially allows protons or positively charged cations to pass, and not other um, uh, negatively charged ions, for instance. So that's just what an H cell is. An electrolyzer would be a more specific term used for an experiment that might use an H cell. For instance, you might use an H cell with an electrolyzer um, to accomplish the electrolysis or the electrolyzer experiments. But the electrolyzer is one. It's you can think of it as the backwards of a fuel cell. If you know what fuel cells are, if you don't know what fuel cells are, then apologies, maybe this isn't that helpful. But it's where you have to. An electrolyzer is a usually two electrode anode cathode system where it requires energy, so like an applied potential to um to 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 operate, I suppose. I'm trying to think of the right word here, but basically, like, again, I always compare it to a fuel cell because it's kind of the opposite of a fuel cell. A fuel cell is a device that has usually two electrodes. That is it's spontaneous, and so what it allows you to do is you're applying fuel over two different electrode materials whose fundamental difference in potential allows you to generate energy from it. So a fuel cell is an energy device, right? It delivers power, energy, current, whatever. Whereas an electrolyzer requires energy to operate, and it usually results in generating a product. So it's like if you're providing, if you're getting energy out of it, that's what it's doing for you. Like a fuel cell gives you energy. Like you can run a car on a fuel cell, right? Or a whatever, have energy, stationary storage from fuel cells, for instance. An electrolyzer, on the other hand, requires you to put energy in. So if something requires energy, it better be doing something for you, because you wouldn't just put energy into something and get nothing out. So usually it makes a product. So an electrolyzer, for instance, might be something where you have water and you have an H cell like this, for instance, and the electrolyzer works in such a way that when you provide more than 1.5 volts of energy across electrodes on both sides, the electrolysis of the electrolyzer might be breaking water apart into hydrogen and oxygen gas. And so the H cell comes into play, for instance. Or it might not be exactly an H cell, but basically a separated cell, because on one side you're generating oxygen and on the other side you're generating hydrogen. It would be usually inadvisable to generate them on the same side or in one solution, in one single not separated solution, for a variety of reasons. But there are commercial electrolyzers that do this. For instance, when I was in graduate school, we had a big unit in our research facility that took water, I think, and generated pressurized hydrogen and oxygen gas for the whole research center. It was really cool. And that's how we got, we didn't buy tanks of hydrogen and oxygen. We had a electrolyzer. And so you could think of it, it's obviously a little more complicated than this, but you can think about it like a giant H cell. Again, specifically, it's more like stacks of fuel cells, sort of, but you can think of it as one giant H cell, where on one side of the H, whatever, it's just zapping water and producing hydrogen gas, which goes into, the plumbing of the building, and then people can use it. And then the other side does the same for oxygen. So that's the difference between an H cell and an electrolyzer. Hopefully that clears it up for you. Avengers. I missed the Avengers. I really like the Avengers movies and everything. I haven't really watched much of Marvel in a long time, but I remember the Avengers series. And I know your question is about what a salt bridge is, but your name, your YouTube handle here is making me nostalgic for, some Avengers, Infinity War, and Endgame, and all that stuff. So thank you for that. But more to the point of your question, what is a salt bridge? A salt bridge is a way to isolate. That's not the right word. Separate the reference electrode from the main solution, the main electrochemical cell that you're studying. So it'll be something like this. This one. Share this one. And I'm sharing. Good. So if you have an electrochemical cell, here's my electrochemical cell with my solution, and I have a working electrode, whatever it is, and I have a counter electrode, okay, and I have a reference electrode. All right, here's my reference electrode. So I have like some silver chloride reference electrode, right? There it is. And this is all in solution. But let's say for some reason, I can't put this reference electrode directly into this solution. There might be a lot of reasons for this. It might be at high temperature. You don't generally want reference electrodes at high temperature. It might be because it's the reference electrode has chloride in the fill solution. You don't want chloride getting into your main solution. It might be because your main solution has chloride. You don't want chloride getting into your reference electrode. Could be contamination either direction. Could be any of a number of things. So what I'm going to do is I'm not going to put the reference electrode in solution. What I'm going to do instead is I'm going to take a tube. Okay. Sometimes it's like you'll put like a fritted tube here, like a fritted glass tube. Sometimes it's just literally a tube, like a plastic tube of some kind. Okay, I'm gonna snake it off to the different location on my lab bench, and usually it goes into something like a cylinder, like a graduated cylinder of some kind, or just some other sort of secondary thing. I'll just draw a little cylinder here just for good measure. Doesn't really matter exactly what it is, but so it's got some secondary whatever compartment, and my reference electrode will go in here. So this is where I'll put my reference electrode. Okay. And so it's separated, right? And I have to have continuous solution one way or another. It could be the same solution in electrolyte as is in the main one, or this could be different than the main one for the reasons that I mentioned. You might not want to have chloride, so you might have like some transitional, I don't know, like a nitrate solution or whatever. I'm just anything. That could be it. And if this whole, for instance, thing is heated, and so I have this, heated up here, and so my whole solution is hot. Well, by the time it gets all the way down, to the end here, it's see, you like this? I'm using color from red to yellow. Now it's cool. That's a cool effect. I'm a very good artist, by the way. By the time that the solution makes it to the salt bridge over here, the reference electrode is not experiencing the high temperature, so maybe you get a temperature gradient, and that helps protect the reference electrode. So those are some of the reasons that you would use a salt bridge, but fundamentally a salt bridge is a way to separate / isolate the reference electrode from your main solution. Okay, let me see, where am I at here? Ibrahim looks like a couple of questions. I did an EIS measurement on stainless steel. All I see from the Nyquist plot is just kind of straight line. Okay. I also performed some measurements on PVD-coated steel, and also the same behavior as stainless. Physical vapor deposition, is that what PVD is? I think so. So I guess the question is, what did you PVD onto the steel if you're not seeing anything? I was expecting a different behavior, like, for example, what is it here? Sorry, I lost my, yeah, there we go. 2 time constants. Okay, what could be the possible reason? Why is there no consensus on which model to use for corrosion studies in literature? Okay, so first of all, why didn't you see anything different? That probably has something to do with, I would say, one of 2 things. One, the PVD didn't work. I obviously don't know. I mean, I don't know your process very well. You'd know better than I would. Check that the physical vapor does. I assume that's physical vapor deposition, and you use stainless steel. So stainless steel might be hard to coat on. I don't know. Maybe not. Maybe carbon steel's easier to coat on. I'm just wondering if, for example, the material you coated isn't like it could be something to do with the PVD. Like it could be any of I don't know enough details, right? So I'm just making a lot of guesses here. It could be that the material is not like conductive enough, and so it doesn't even like measure it, right? Like you have steel, and that's the primary um, response or whatever, and then you put some physical vapor deposition, some film, some material onto the stainless, but it's not like electrochemically active or measurable, and so you're just measuring the same steel twice, even though you have some film. Like the film might be passive as it relates to electrochemical signals, for example. Yeah, physical vapor deposition. Thanks for confirming. I thought I had it right. I've never done PVD, so I just don't have a ton of like personal experience with it. In any case, so that's a possibility. Maybe the film is so thin it's not picking it up. Something like that. If it's something that's supposed to be corroding, maybe the PVD film is not adhering. I know PVD is, or I believe PVD. It's not. There might not be a binder, something like that. Uh, you know, maybe the film has delaminated. Uh, any of these are possibilities as to explain why you're seeing the same behavior, roughly speaking, right? So that might be something to look into is the process. As far as not having consensus on which model to use for corrosion studies, well, first of all, there's a lot of different materials that people are studying corrosion on. People are often studying things like the inhibition of corrosion, and so they're looking at different, I don't know, biopolymer films and things like that to coat the sample to prevent corrosion, and you're going to get a lot of different kinds of processes there. And so there's going to be probably no consensus when all of the data are quite different, right? If the corrosion that's occurring on materials are very different, then of course the models might be different and the mechanism for corrosion might be different. For example, the corrosion on 1018 carbon steel is going to be very different than the corrosion on 303 stainless steel, which is to say there's almost no corrosion on stainless steel. It's stainless, right? But like low carbon steel, or non-stainless steels. I don't know. There's a lot of different varieties of steel, of course, are going to corrode faster than stainless or Hastelloy or 303 or 304 or 316 or 1010, right? Anyway, there's a million different flavors of steel and stainless steel. I don't need to name all of them, but so that might be one reason for confusion. Like, well, why can't everybody use the same model? Well, because everything kind of corrodes differently. And then, of course, if you're studying corrosion, there's almost always slightly different media. You're using 3.5% brine, and this person is using, a biological sample from the ocean or something. I mean, there's so many different varieties of test, right? That it's probably not possible to get a uniform, model, because how it's all happening is going to vary by quite a lot, I would say. But there are usually some overlaps, right? I mean, like you said, once you maybe look into this PVD experiment that you're looking at, you might be able to eventually work your way to finding impedance results with time constants, like with Randall's elements or whatever you're looking for. Maybe the process will help clear that up. The other thing I forgot to mention is that because you're working with stainless steel, and stainless steel doesn't corrode very easily or almost at all, right? You might have to polarize your sample like a decent amount. So I guess I would have a general question, and I'm I'm just making the assumption. I could be wrong. You can correct me if I'm wrong. I'm guessing you're doing corrosion at open circuit potential. So you have your stainless steel sample, whether it's the PVD version or not, and you're just kind of running impedance at open circuit, and you're getting a straight line, which is mostly just capacitance without any real corrosion. Because stainless steel is sort of fundamentally resistant to corrosion, right? Hence, it's stainless. It's designed for that purpose mainly. You might have to apply a bias to get it to corrode more quickly to be able to measure it. So you might need to do something like try using as your baseline instead of open circuit potential, try like 100 millivolts versus OCP or 200. I don't know how high you'll have to go, to be honest. But you can try several hundred millivolts versus OCP positive. That might induce corrosion so that you can study it, right? Because if you're getting impedance and you're trying to study the impedance of the corrosion, but it's not corroding, well, you're not studying corrosion. So you might have to have a bias or a set point for your measurements to be able to adequately study the process of interest. So you might try that, just even before you fiddle with the PVD, process a little more, I guess, is try to add some extra, over potential to the oxidation process and see if that helps induce the corrosion a little bit more. Okay. Good to see you, my friend. Favorite American electrochemist. That's high praise. I will not tell Tim and Alex that you said that. They would be deeply offended. Good to see you. Okay, so Amira, yes, electrolyzer and H cell discussion. So basically, electrolyzer is the general term, but H cell is also. Electrolyzer is the general term for a thing that I described, like that's like splitting water into hydrogen and oxygen. It's a device. It's a general term for a device. Yes, and H cell is not an electrolyzer. And H cell is the hardware, the physical hardware that I showed you, like the picture of on my website just a moment ago. They're not really. An electrolyzer can use an H cell. An H cell is just a physical thing. It's a cell. It's a design. It's a I don't know, structure that can be used. It's not always glass, by the way, but glass is pretty common. It's a structure that can hold an electrochemical experiment, just like a glass or a cell or anything, right? I'm trying to kind of clarify this. It's like the electrolyzer is the electrochemical device. An H cell is just a vessel. I hope that's clear. I think I'm trying to just make sure this is not too confusing. In other words, they're not really. They're two different things, right? They're not comparable, for example, like directly. One is a vessel and one is a device. I don't know, something like that. I won't tell them. Don't you worry, Tarek. I won't tell them. But they might watch this. Alex might watch this, and he's going to be very upset. But that's just too bad, because we all know who the favorite is. Oh, that's funny stuff. So, okay, I think at the moment there are no fresh questions other than the declaration of being the favorite American electrochemist, which is wonderful. So, I think what I'll do is take this time to. Gurab had asked earlier about explaining EIS. I think what I'll do is I'll just talk through very briefly some of the content I had shared in one of my webinars, for example, about impedance theory, to address this question. Basically, what is impedance? Is that what it is? Sorry, I just had the question and I lost it. Is it just generally, can you explain impedance? I think is the question. I keep going past it for some reason. Yes, can you explain EIS? Yeah, so it is a general question, to be fair. It's not something that's maybe quite easily answered, I suppose. But what I'll do is I'll just talk through how it's done. I'm not going to talk through all of my slides. It's a bit, to be honest, it's a bit much. So let me just do that. And then in the meantime, if there are any other questions, please type them in. But this will be the last thing that I show for today. Again, unless there are any questions, I'll try to talk through this for just a bit, and then we'll call it a day, I suppose. So, okay, let me make sure that my face is out of the way as well, because that's always fun. Move myself over here. So, explaining impedance, right? I've talked a little bit about why you would do impedance. You deconvolute signals. And all of that good stuff. But what is it? How do you do impedance? Fundamentally, you have an electrochemical system, and what you do is apply an input signal that is a sine wave of potential. It has this form, so E of t is equal to E naught sine of omega t. So we have the amplitude of the signal, which is called the peak. We also have RMS and peak to peak are different ways of representing the amplitude. For instance, most commonly you would use peak, and the period is 1 over the frequency. So this is basically the input signal of an impedance experiment. A potentiostatic impedance experiment is a sine wave of potential. The output, if the input is potential, is a current sine wave. So we have an output that has the same frequency. I of t is equal to I naught sine of omega t. And then it may be shifted by a phase angle, phi or phi, and it has its own amplitude. And so what we do with an impedance experiment is we send high frequency, then low, then low, then low, and then we're done. So an impedance experiment fundamentally involves sending different frequencies of sine waves, usually from fast to slow, usually of potential, and then we're measuring current into our system, and then we finish it. When we look at the signals, they are called Lissajous plots, and they typically look something like this. It's kind of like a cyclic voltammogram for impedance, but it's usually over a smaller range of potentials to make sure that it is linear. Okay. And then very briefly, what we do is we analyze the signals. We get the impedance magnitude, which is analogous to Ohm's law. So the ratio of the amplitudes of the potential and current gives us the impedance magnitude. The phase shift is what I showed. It's the difference between the input and the output signals. When we do a little bit of mathematics, what we do is we get real and imaginary components of the impedance magnitude and the phase angle, Z real and Z imaginary. And so when we are finished with an impedance experiment, we get 5 columns of data. We get frequency, Z real, Z imaginary, magnitude of the impedance, and the phase shift. We get these 5 columns of data. This is the last bit that I will talk about, because again, most of what I'm showing you here is part of a webinar that you can see the whole content in a little bit more detail on our YouTube channel. And basically, we make Nyquist plots, which is where we plot the real and imaginary impedance. We make Bode plots where we plot the other 3 variables. And so we have frequency, Zmag, and phase angle. And that's the as much, I think, as I will explain, quote unquote, impedance at the moment. That's how you apply the signals, and then how you analyze them and how you plot them. Again, I'm just talking very quickly through that. For a better and more thorough explanation, I would encourage you to check out my my webinar from earlier this month, or any of the impedance webinar recordings that are on our YouTube channel. Let's see. So yes, Amira, I was wondering because during your response you spoke about Nafion membranes being used in PEM electrolyzer. However, I saw several articles using Nafion and KOH. I didn't understand why. Yeah, I think the reason why is because there are not, to my knowledge, a lot of commercial options for alkaline membranes just yet. There is and I actually have some experience with this, because when I was in graduate school, I studied alkaline electrochemistry. And it's difficult in a lot of ways, because alkaline is in many cases more corrosive than acid. And it makes it harder to find materials that will work. And then the other sort of thing there about that is that Nafion is the state of the art, material basically for like PEM fuel cells, right? Or PEM electrolyzers. And it's brilliant, right? It's stable. It's accessible. Almost everybody can purchase it in research labs everywhere. And it's fundamentally a polymer molecule that has I always forget, is it sulfur or phosphorus? Nafion structure. It has positive sulfur, I think, right? Sulfur, sulfonic acid groups. And so in any case, it's like a PTFE backbone with a sulfonic. Yeah. Okay. So it's got these negatively charged ligands or something like that. Like I said, I'm more of an alkaline electrochemist, so my great knowledge of Nafion is a little lacking, let's just say. But roughly speaking, it's got negatively charged ligands, and so it attracts positively charged protons, and it can shuttle them through. It kind of begs the question, if it has negatively charged like ligands that naturally attract protons, right? And that can travel through because there's an attraction between negative charges. How can Nafion adequately shuttle hydroxide? Because it's got negative charged, ligands, and hydroxide is negatively charged. So how would it even work? I think the answer lies somewhere in the fact that it's just also a semi-permeable membrane, like in and of itself. So despite the sort of wrong, valence charge or whatever of Nafion compared with like hydroxide, it still acts as a permeable membrane. I do also believe that over some period of time, it will degrade in hydroxide. It might start kind of corroding. And it's like if the membrane corrodes, it might as well not be there, right? You'll just have crossover. You'll have, it won't be a membrane anymore. You'll just have holes in it or something like that. I think it depends on the length of exposure and the concentration of hydroxide. So maybe if you have dilute KOH, it won't be a problem for some period of time. But for whatever reason, there just hasn't been, I don't know, maybe a commercial breakthrough option for a membrane for alkaline electrochemical electrolyzers or fuel cells, like mass produced in the way that Nafion has been. I think that's kind of what it is. I always like to sort of plug Professor Dr. John Varco. I think he's still doing work in this area, but my work in graduate school, we had some collaboration with John Varco. He is in the UK. I think the University of Surrey. Again, if he's still there, he may not be. I'm not positive. I haven't been in this field in quite some time, but he has done some brilliant work on anion, like alkaline ionomers in membranes. And his group, for example, has made them. I don't know if they're commercialized yet. That's why I always sort of hesitate. Like, I don't think that there's mass-produced commercial options. I don't know if he has done some of this. I know that like when I was in graduate school, my advisor knew John pretty well. And so he sent us from time to time, like some of the membranes that he synthesized in his lab over in England. And so we had the privilege of getting to use some of those, which was really nice. But again, it's like, other than that, if you don't have that connection or there's no way to purchase them easily, we're sort of stuck using something like Nafion, because it's like, well, what else can you use? You can use just polypropylene or polyethylene, sort of some general polymer plastic of some kind. Yeah, it's a bit of a tricky thing. Again, I think that the reason people are using Nafion for the most part is just because there aren't any really, I don't know, available options. Because technically, I would propose that Nafion isn't the best solution for alkaline electrochemistry. It's not really built for that. It's built for acid and proton exchange. So, alas, we are we are electrochemists and we are sort of stuck with what is available to us. And a lot of times that thing is just Nafion. So we're stuck using Nafion. Well, I think that's going to do it for me for today. I do think that I've got to all the questions. Let me just scroll up just a bit and make sure that I've got everything. I think I have. So with that being said, thank you everybody for the questions. Thank you for showing up. I do appreciate it. I'm glad that people were able to join here. Sustain ion and Fumasep are not as famous as Nafion, but good options for AM. Yeah, I knew there might be something. Okay, so Fumasep or sustain ion. Yeah. I wonder where I haven't heard of these, or maybe I have, but it's been like in passing. Like I said, there might be the better commercial options. They're just not as famous. Nafion's more famous because any commercial, if there are any commercial solutions for fuel cells, are usually PEM, and they mostly use Nafion. So, but anyway, I'm glad to see that there are some commercial options for AEMs. And so, yeah, I hope that if you're doing alkaline electrochemistry, you're able to get those. So anyway, as I was saying, thank you, everybody. I do appreciate it. I hope everybody has a great weekend or rest of your Friday, depending on where you are in the world, of course. And thank you again, everybody. I think next week, I think me and Alex will both be here, but always hard to tell. One of us is traveling somewhere a lot of the time anyway, but we always do try to be with you each week. So that being said, again, appreciate everybody's input and questions, and hope this was helpful to everybody. If you have a question that wasn't answered, please leave it in leave a comment in the below and on our YouTube channel, and the timestamps will be in the description as well for all the questions that I answered today. So everybody, I hope you have a great weekend again. Take care. We'll see you next time.